Hello everybody. Going against your poll that we did on Edmodo to determine how you'd like me to deliver extra content. Majority of you voted that you'd rather just a voice clip over some of the slides. However, I'm going to make these videos pretty short so they're easy to digest and get through. So I'm going to be making 3 videos, one for essentially each lesson of the week. The first one is going to be on special relativity. What is it? What are the postulates of Einstein's theory? And what is a frame of reference? The second video we do is going to be on relative motion and how does that compare to what Newton believed. And the third video is going to cover simultaneous events and what is meant by simultaneity. So let's get started. A lot of this stuff is based off your textbook, so if you are keen for more information, just head to chapter 9 and look at the time and motion section. So special relativity. So a couple of centuries after Newton came out and said, hey, here's all the ways I think I can explain mechanics and motion and whatnot, pretty much everything could be explained using Newton's theories and his approaches. Now, by the end of the 19th century, so the end of the 1800s, we started to come up with a couple of situations where Newton just couldn't explain a few things, okay? And in the 1940s, there was a problem with being able to account for how long this particle called a muon was able to exist for at different altitudes, etc. Okay. Now, this was a great example of how we can research into it to look at and go, hey, was relativity or is relativity actually real? Have they proven it? How can you prove relativity, etc.? And this study on muons is great for that. So, what is a muon? Okay, we'll get into that. So a muon is just a small particle that occurs when some particles collide. So to summarize this for you, you essentially have cosmic rays that hit an atmosphere containing oxygen and nitrogen. Once the sun hits that atmosphere, it creates something called a pion. A pion then decays into a muon, and a bit longer after, a muon will decay into an electron. Okay, and essentially, these things are traveling at the speed of light. Okay, almost. They're 0.99 or 99% the speed of light. So cosmic rays hit the atmosphere, we get pions, pions decay to get muons, and muons will essentially rain down on over our Earth. Okay, now these should only live for 2.2 microseconds, so 2.2 times 10 to the minus 6. Okay, it is very, very small until they decay into an electron. It is not a long amount of time. So, our rays come in, we've got our muons raining down, but by the time it hits the ground, everything should have decayed, and we essentially just have electrons coming down. So here's the problem with that. In 1962, there were 2 physicists, okay, from MIT, and they were experimenting to prove to students that relativity is real, okay, and that we need relativity to solve this bit of a problem that everyone was having in the 1940s with muons and why they didn't live as long as they thought they did, or how far they could travel, etc. So what they did is they went up to top of a mountain, Mount Washington, which is 1,910 meters above the ground, and they put this device out there and they measured how many muons are they actually getting through this device in an hour, and they measured 563. They then went down to the bottom of the mountain, so at sea level, and theoretically from standard Newtonian calculations, Newtonian mechanics, if we think about speed, distance, time, etc. Okay, if they're traveling at 0.99 the speed of light, it should only take 6.4 microseconds for them to travel the 1,910 meters from the top of that Mount Washington to sea level. Okay, and considering they decay in 2.2 seconds, nearly everything should have decayed by the time it gets from the top of the mountain to the bottom. So in theory, those 563 muons that came through their device at the top of the mountain should have pretty much all decayed by the bottom. However, when they took their device to the bottom, okay, and measured it, they should have had about 27 in an hour. However, they measured 409, and that is what was predicted by relativity. So from Newtonian mechanics, we should have got about 207, which is not the case. From what they measured, they got 409, which is very, very important for actually confirming that special relativity exists. Okay. So this is a great way to explain relativity and some of the theories that Einstein came up with relating to relativity. And I've got some dot points and I'll try and explain them. If you can't understand them, it's okay. You just have to have faith, and we will explain in more detail soon. Okay, so we're going to need to look at a frame of reference. and what it means, and we'll look at that in more depth in a bit. But essentially, it's what they're comparing it to. So according to the scientists, comparing where the scientist is at the bottom, comparing to the top of the mountain, from their frame of reference, in other words, what they're referring to, is a distance of 1,910 meters. Now, look from a muon's perspective, if we were a muon and we were traveling to the bottom of this mountain, from the muon to the bottom of the mountain, they're actually only seeing 183 meters to travel. Okay? From their frame of reference, it's 183 meters. Who is right? They're both right. It depends on what your frame of reference is, what you are referring to. Again, we'll cover that in more detail soon. So essentially, muons didn't have to travel 1,910 meters like the scientists were seeing. They could see themselves at the top of the mountain, 1,910 meters. They only had to travel 183 meters because that's what they were seeing from where the muon is to the floor, or to sea level. So this basically helps to confirm Einstein's theory and his prediction of length contraction. Okay, we'll get more into that soon. So let's look at time now. We looked at length and how length changes. Let's look at time. From the muon's frame of reference, that only took them 2.2 microseconds. It didn't take them very long. It was only 2.2 microseconds that they were alive for. However, according to the scientist's frame of reference, the muons are able to live for 23 microseconds. Okay. Now this means that from the scientist's frame of reference, it's 23 microseconds. So of course they're not going to decay in that 6.4 microseconds that it takes them to get from that top of the mountain at 1,910 meters to the bottom of the mountain. Okay. Again, muons thought it was 2.2 seconds. Scientists observed 23 microseconds. Who is correct? They're both correct. It depends on their frame of reference. Now, this helps to prove Einstein's theory and his prediction of time dilation and how time changes and stretches out, okay, as we start to approach the speed of light. We will cover that in more detail. But as you can see, what is essential here, and this is what we're going to cover this lesson, is what is a frame of reference. So, a frame of reference is essentially just a place that you compare it to, and it is critical when we explain this muon experiment. Now, when a car drives past at 60 k's an hour, you're going to picture that you are in the car, right? You are in a car driving at 60 k's an hour. And when I refer to the ground, and my frame of reference is the ground, okay, I am traveling 60 k's an hour with respect to the ground. When I compare myself to the car, I am traveling at 0 kilometers an hour compared to the car. Which is correct? Technically, they're both correct. So we need to make sure we understand what a frame of reference is. Okay, it is just some sort of abstract coordinate that we compare things to, and obviously it's required because it can produce vastly different lengths, times, and so on. So there's two types of frames. Okay, there's an inertial reference frame and a non-inertial reference frame. Okay, essentially we can summarize it to this. Okay, an inertial reference frame has no acceleration. A non-inertial reference frame actually has acceleration. So if you have a constant velocity, okay, it is inertial, or even no velocity, it's inertial. If there's any change in velocity, therefore there's any acceleration, it is non-inertial. Okay, an example is usually used of dice in a car, for example, or anything. If you're traveling at a constant speed, if you had something hanging from your mirror, it would stay completely stationary like this. It might move around a little bit, but if you accelerate, it's obviously going to swing back as you accelerate. If you slam the brakes on, it's going to swing forwards. Okay, you don't want that. Okay, we don't want to be referring to non-inertial frames because all the special relativity we're going to be looking at inertial reference frames. Okay, so inertial, our place that we compare it to, our frame, our object, constant velocity, even if that's 0 velocity. Non-inertial, not constant velocity. Okay, here's some examples you can look at. So, an example is the gravitron. If you're riding in the gravitron, it spins at a constant speed. Is this an inertial reference frame? Well, you have to think of all the different scenarios, okay? If you were on a gravitron and it was spinning, would your keys be hanging still like this? Hell no, they'd be spinning outwards. Okay, because you're sitting there and you'd be stuck against the wall. Your keys would also be swinging outwards too. Okay, that still has acceleration. It is just centripetal acceleration. Okay, so to actually see whether or not we can, or to actually come up with this special relativity, to make sure special relativity holds true, there's two things that need to actually be true for this theory to be, well, true itself. Okay, and they're called postulates. And essentially, number one is physics is the same in all inertial reference frames. Well, yeah, it is. Number two is light is the same speed in a vacuum in all inertial frames. Well, yes, it is. Okay, you need to make sure you remember those. Okay, so here's a couple of questions I want you to go through. Essentially, the summary is, what is special relativity and how does it work? Do you know what a reference frame is, non-inertial and inertial? And do you know the two postulates for special relativity?